Yeah, so recording has started. So in the last class, we have started our discussion on these topics. We have discussed this effort delay. We have discussed the general, what should be the general expression for delay in any combinational circuit. And while discussing this topic, we have introduced a couple of new parameters. One of them is the logical effort. Other one is the fan out. Fan out, obviously, fan out or the electrical effort, and parasitic delay. Parasitic delay also but we have used it earlier as, or we have described this delay as intrinsic delay, right? Not as this. So here, while discussing the logical effort, we have discussed how to find logical effort and what should be the logical effort for commonly used digital gates, right? Then we have discussed about the parasitic delay, and we have also seen how to find parasitic delay for any other gates, right? So basically it would be in comparison with that of this inverter, right? So and while doing so, after that we have also finally ended our class with here. We have tried to plot it here, this normalized delay versus electrical effort, right? So I have seen that how this normalized delay versus electrical effort while a particular gate is driving the same gates would look like, right? Where we have also seen that this y-intercept denotes the parasitic delay, and the slope indicates the G or the logical effort, right? Okay. So then let us start our discussion for today's class from here. So it says that delay in a multi-stage logic network. So here you can see the logic is like this. So starting from this NAND gate, then we have NOR, NAND, then again an inverter. And finally it is driving a 20 or a load capacitance whose value is of 20 of C into C minimum. But we generally do not mention of C minimum. We always say it is 20, means it is understood that 20 of C minimum. Okay. So then here we need to optimize what would be the minimum delay, okay, or what should be the sizing of this X and Y or Z, so that we will get the minimum delay. And here I think you have already noticed that when you are saying it as 10, so 10 means is the input cap is 10, right? So input cap is 10. So input cap means it consists of the PMOS as well as the NMOS. So that total capacitance input consists of this 10 unit, right? Okay. So here the techniques that we are going to follow is quite straightforward. So first see the technique. I think you will understand it. It's not difficult. So a couple of things we have to find. So you have to find the logical effort. Now it is a complete path. Logical effort for an individual gate, but it's a complete path. So and the path has been shown here by this dotted line. So here this is the path. So right, and we have to find what is this path logical effort. Right. So path logical effort, we denote it as capital G, and this would be the multiplication of all the G's of through means whatever is present in this path. Right. So if you have to do that, then this pi of G. So let us first. So here what is G? You can say like G1. G1 is equal to 1. Here this is G2. This is 2 input NOR gate. So it is 5 by 3. We have done it yesterday. G3 is equal to 4 by 3. This is G4, again NOT gate, so this is 1, right? Then after that we also know that we have to also find this H. I think you can recall the H is basically fan out, but it is not driving the same gate, so the fan out would be the output cap by the input cap. So here H1 output cap is X, right, by this input is this size is 10. Right. Here this H2 is Y by X. Here H3 is Z by Y, and here H4 is 20 by Z. Okay. So then what we have to do here, this 1, like we have to just, it is a multiplication of all this G. So it is 1 cross 5 by 3 cross 4 by 3 cross 1. So it is 20 by 9. So this is the total path logical effort, right? Similarly, we have to find what is the path electrical effort. Path electrical effort, and that is denoted as capital H. So that capital H would be given as this C out of this path. So what is the output capacitance in this path? Output capacitance is the final capacitance. So that is equal to 20 by C input of this path. That is the input capacitance in this path. So here it is 10. You can see this is 10. So this value of capital H is 2. Right. And you can see here there is no branch. I think the concept of branching we have discussed briefly last class, means there can be like one more line here with this, one more NAND gate or any other gate might be attached. So that path is not there, right? Because it has no branch, right? So if no branch, like for this case, then this capital F, I hope that you recall what is capital F. Capital F is the effort delay. This effort delay is given as G into H. Right, just multiplication of this G and H. So if you do that, it is 40 by 9. Okay. So this is the effort delay. Right. So, but you know that for a path, what will be the total delay? Total delay should include parasitic delay plus the effort delay, right? So probably we can write it like this: total delay would be the parasitic delay, like we have to add all the parasitic delay for all these gates, plus we need to add all the effort delay. This is the path effort delay, right? This is the path effort delay, but this is the like individual level gate delays, isn't it? Okay. Now, if you recall, when we have done to estimate what would be the minimum delay for the chain of inverters, then we have seen the minimum delay would possible when the each states bear the same effort, right? You recall, right? Means if it is a chain of inverter, and it has to drive a cap of, suppose say like CL, then, and suppose this is 1, then maybe you are multiplying it with F, right? Then this size become F, then next you have to multiply with again F, then this size become F square. Right, we have seen that, right? Then only the minimum delay will occur. Basically, what you have to do, you have to take a partial differentiate, like for each individual step, and make it equal to 0. Like similarly, what we have done here. The same thing is also applied here. If you do that, it will come that the minimum delay will occur, or the delay would be minimum when each stage bears same effort. So maybe for your reference, I will write that as well. So path delay is minimum when each stage bears same effort. Okay. So now we have seen this would be the criteria for minimum delay. That path delay would be minimum when each stage bears the same effort. and say that same effort is F. Okay, say that same effort is F. Okay, so and it has how many stages? Say n number of stages, right? Then we can write this F into F dot 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 this n times. If there are n number of stages, I think we are writing small n, so we will write it as small only. This n times, right? So that would be equal to the total F, right? This is for the total path, like this is the path effort delay, right? So this should be equal to capital F. So that means this is f to the power n is equal to f, or f is equal to nth root of f, right? So if you want to find it like for this particular case, then what would be the value of this f? F would be equal to nth root. N is basically 4, I think here 4. How many stages? 1, 1, 2, 3, 4. N is equal to 4 here, right? So fourth stage, so it is 4 root of what? Total f is 40 by 9, right? So if you calculate it, probably it will get, you will get it 1.45. Okay, so then the effort of each state should be equal to f, which is 1.4 times. So that means whatever be the size, compared to that you have to multiply, means the next capacitance should be 1.45 times. Compared to this capacitance should be 1.45 times. Same thing goes for from here to here. Okay, now this is the criteria. Okay, this is the criteria for F, which will give you the minimum delay. Right? Now we also know, I think we have already done this. Let me check it out here. Yes. So here we can see in general we have written here this D, the total delay, is equal to the parasitic delay plus this effort delay, right? So here too we can write the total delay, that is capital D, that we have written in terms of individual delay, parasitic delay plus the total. So this is basically the parasitic delay, so we will write it better like summation of all this parasitic delay and this summation of all this f, right? Okay, now summation of all this f, if we write, then it will become how much? We have seen f is 1.45 times, so it will be 4 into 1.45, right? Summation of, if you do that. Now what is the total parasitic delay? Total parasitic delay here is equal to, we have to see, this is inverter, so for inverter parasitic delay is 1, for NOR 2 input NOR it is 2, 2 input NAND it is 2, again inverter it is 1, so the total parasitic delay is 6, right? So basically this is the summation of P, right? So you can put it here 6, so it is 6 plus this much, so this would be 11.8 unit, right? So basically we are using the normalized delay, right? So it would be 11.8 unit. So please let me tell me whether you have understood the process or not. Have you understood the process?
Sir,
Okay, so if you have understood this process, fine.
I have a
So,
doubt.
okay,
So here you are saying total delay is summation of PIs and FI.
total delays,
Summation of all PIs and FI.
right, all PIs and right.
FI.
Phi means
So,
it is basically like, okay, better to say like summation of F. Okay,
okay.
right, right.
So yesterday there was an example like one inverter and then some inverters in branching.
Hmm.
So for that, why didn't we add all the PI or FI?
Right. So for this example, we do not have any branching, right? So we have written this one explicitly here, right? Here it is no branch, right?
Yes.
Okay. So for no branching, this F is GH. If you have a branching, then it would become F equal to GBH. Then it would be the path logical effort into the branching effort into the path electrical effort. So it will be a multiplication of all three. But here there is no branching, so that means the branching effort is 1. So here that value is 1. Anyway, the branching one we are going to discuss in the next only. Okay.
No, sir,
So,
I was talking about the total delay.
total delay. But yesterday, which one? I think the last one I was saying here. Give just I have taken one example. Like I have shown it something like this. That
Yeah, 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 yes.
if you have something like this, then what will be the delay, right?
Hmm.
So here we have to introduce the branching effort as well. Okay, so that would be that included in the total delay because see, because this gate has to drive this gate as well as this gate, right? So the delay would be affected. So for in this path only, this transistor, this gate is there and this gate has to drive this, right? So obviously this path delay would be affected because of this branching. If there is no branching, then only this path has to be considered. Then it would not be affected by this path, right? If it is not there. Is this clear to you now?
Yes, sir, yes.
Okay. Okay. So now we have seen like it is quite easy only like how to size this each of these gates, right? But the question is like not how to size means what would be the minimum delay that we have find, but we have not done the sizing it yet. So now we have to find what would be the value of X, what would be the value of Y, and what should be the value of Z. After that, we have to also find what would be the transistor like PMOS width for this, NMOS width, PMOS and NMOS width for this, same thing for this, same thing for this. Right? Because while designing, you have to design in the transistor level, right? So it should be the PMOS width and NMOS width that will matter. So let us now complete that for this circuit. Okay. Now the first what we are going to do is that we have to find what is the value of X, Y and Z. Right? Okay. Now this is our objective is to find X, Y and Z this thing. Okay. So to find this thing, just one thing I think you have already noticed, but just I want to write it again here. See this H. What is H? H is basically equal to in general. Yesterday we have seen it is C out by C in. Fine, right? What is F? F is equal to GH, right? Effort equal to this, right? Fan out into this logical effort. Okay, right. From here, we can write C in equal to C out by H, right? Now we can just substitute the value of H from this. So basically it is H is equal to F by G. So G will come above, H will go here, right? So basically it says that C in would be equal to C out into G by H. Now why I am doing it?
Sir,
Because we need, Yes,
Sir, it would be G by F, right? We are replacing H.
right, right, yes. So G by F, right? So why we are doing it or representing it like this? Because see here, we know what is C out. C out means what is the final capacitance here? That is basically the C out. We'll start from here. Okay, C out. Then we know what is the value of G, and we know what is the value of G for this gate, and we also know what is the value of F for this gate, right? So here you see we know C out, we know G, we know F for the last gate, right? And if we know all these things, we can find the value of C in. And what is C in? C in is nothing but that sizing this jet, right? That's what I told you. Here this 10 means the total capacitance of total capacitance offered by this inverter, right? So here we will start from this Z. So that Z would be equal to C out. So if you see this here, C out is equal to 20, right? 20 into G is 1 by F. F is 1.45 for all stages. We have already seen 1.45. So 20 cross 1 by 1.45. So that would give you 13.79. So the value of Z should be 13.79. In the same way, you can find Y. Now Y we have started from here because we know this, right? Now we know this, we know G and F this, so we can find what is the input cap of this, right? Now this gate is driving this, this NAND gate is driving this inverter. So for this NAND gate, this C out would be the input capacitance of this inverter, right? But now we know what is the input capacitance of this inverter. So that is basically the C out for this NAND gate, right? Okay. So here this Y will be C out. C out is this one 13.79 into G. So for NAND gate, G is to input NAND gate 4 by 3 by F. F is same 1.45 for all of them. So it would give you 12.68. Now we know why. Y means what is the input cap seen by this, right? Okay. So what is the input? Okay. Remember when I am saying the input cap means for only one input. Okay, it's not the total capacitance because it has like two gates, right? So if one if because this is driving only one of the input, right? So if you have suppose shorted this one, then the scenario would be different. I hope you are able to follow me what I am trying to say. Here this is driving only one PMOS and one NMOS, right? And the size indicates that total capacitance offered by that PMOS and NMOS, right? So it is not the total capacitance offered by the complete like two input NAND gate because it has two input. If you connect something else here, whatever be the capacitance you are looking or seeing from here, the same capacitance you will also see from here. But that should not bother us because we are considering the path is this, right? Okay, so now we know what is the capacitance, input capacitance here. So that would be the output capacitance for this NOR gate. So we know C out from here. This C out is basically 12.68. So here we will find X. X is equal to 12.68 into for NOR gate G is 5 by 3 by 1.45 which will give you 14.57. Okay, let us now just for verification do one more thing. Okay, so we know the cap for this, like capacitor for this. Now this inverter is driving this like this output node capacitance, right? Even though the size is mentioned here, but let us try to calculate and see that whether it is matching with 10 or not, right? So let us try to find what would be the first inverter size. or size of first inverter, better. Size of first inverter. So that would be equal to, this is the output capacitance the first inverter is driving. Its what is this G value? G value is 1, that is logical effort is 1 by its the F value. F value is 1.45. So you can clearly see from here what you will get is 10. So that is already, the size has already been given here, na 10. So you can see that. So you have just checked it in a reverse way, and we have found that this size is 10. Right. Any question? Any question? Okay. Now, so these are about like the gate level sizing, XYZ sizing to find, right? Now we have to do the transistor sizing. So how we will do that transistor sizing? Now, this is a transistor sizing, right? So again we'll maybe now we can start from any place. Just a minute. We can start from any place. We can start from this or from this. Let us start from this last inverter only. Okay. So transistor sizing for the inverter. So for this inverter, it is given P by N ratio, means width ratio, right? This is equal to 2:1, right? And this is basically the size of the inverter. Size means basically the total input capacitance, right? For a single input. So it is 13.79, right? Among which 2 goes for PMOS, 1 goes for NMOS. So from here, so for stage 4. So for stage 4, which is basically an inverter, stage 4 inverter, PMOS width would be equal to 13.79 into 2/3. So anyway, you can calculate it, right? For NMOS width, it would be 13.79 into 1/3. Same goes for stage 3. I think it was NAND gate, right? PMOS width would be equal to, so the size is 12.68 now. For NAND gate, that is the 2 input NAND gate, here PMOS by NMOS ratio generally this is what? Okay, what would be the ratio of PMOS and NMOS in terms of width? Yes, students, please do respond.
1:1.
1:2. Okay, see, like, but what is the actual width? Is it 1?
2:2. Both
2, right? 2:2. Yeah, we can always write 2:2 as 1, but okay, it is like 2:2, right? So from here, it would be then, you can clearly see, like it would be basically 2/4, and NMOS width would be equal to basically half of it, right? 12.68 into half, right? Okay, now here for stage 2, this is 2 NOR gate. So for NOR gate, what is the ratio of PMOS and NMOS? I think we have done it already. So it is 4:1, right? So PMOS width would be equal to, this is the size, 14.57 into 4/5 NMOS width would be equal to 14.57 1 by 5. So you can see it is pretty straightforward, right? How can you like if you want to do that, right? Similarly, if you want to do for the first inverter, it is 10, and for inverter it is like 2:1. So you can find the width for the PMOS and NMOS for the first inverter as well, right? So now please tell me which part is not clear to you. Okay, so if these things are clear to you, fine. Then let us move to the next one. That is considered the path branching. Now you can see we have an inverter here. Size is 5. It is driving two inverters which are in parallel, size of 15, and each is driving a load of 90. Okay, and but we have to consider a path, right? When we are considering a delay, we should always mention about the path. So this is the path, right? Okay. So as I already mentioned, so when you have a branching, so basically then first observation is branching present, right? Here. So if branching is present, we have to introduce a term which is called the branching effort. Branching effort, right? B. So branching effort is denoted like this. Called capacitance for the on path plus capacitance for this off path by the capacitance of this on path, right? It's pretty straightforward. So I have to find the what is the capacitance in this on path by capacitance in this off path by capacitance in the on path. Now you will also see that how to find and all this stuff here. Okay, maybe let us find it here. So what is the capacitance for on path? So on path, if we like when you are mentioning the capacitance, so capacitance means for this inverter it is has to drive this and this, right? So when this inverter is driving this, so the on path means for this means like on this path, the next load for this inverter on this path is this one, so which is 15 plus what is off path. Okay, this inverter whose size is 15 is also been connected with this, right? So inverter has to drive this as well, right? So here this off path is also 15. By on path we have already mentioned 15, so it is basically 2, right? Okay, now earlier we have seen this F equal to GH, but now we have to find it F equal to GBH. Okay, now what is B? It is the path branching effort. So what do you mean by path branching effort? Path branching path branching effort is basically the summation of all the branching effort. So here B is only this, right? But if it can happen, right, after that you have one more branching, right? Then you will have B1 and B2, right? So you have to do a modification of that. So here one thing I should correct, it would be like this. Like we have seen the total G, this G is equal to pi of G, right? So this is a simple example, right, which shows what we have to do if there is a path branching which is present in the path. Now in the following example we will have almost everything. We will have more than one path branching, okay, and we need to find couple of things from here. See, here in this example, please notice, this is the NAND gate. This NAND gate is, this is two input NAND gate. This two input NAND gate is driving three input NAND gate. So you can see here, these NAND gates are 3 input. Okay. And it is given the sizes are same, like XXX. Okay. Now this particular NAND gate, 3 input NAND gate, is driving 2 NOR gate, 2 input NOR gate, right? And 2 input NOR gate, their also size is also same, move I and Y, and each of them are driving like a load capacitance of 45 unit. Okay, and it is mentioned the path is here, means we are interested in this to find the delay in this path or along this path, right? So we have to find what should be the minimum delay, and to achieve that minimum delay, what should be the size of each of this transistor, right? And what should be the size of this PMOS and NMOS for each transistor, right? So this is compared to our earlier example, this, right, compared to our earlier example, this is bit like more like we have more branching and all these things been here. So we'll try to solve this. Okay, so again we will follow the process that we have learned just now, that is what is G. So I am not writing again, G is the path logical effort and all these things, right? So G is equal to, but in exam you should write, okay, please note that in exam it is expected that you will write G is the path branching, like path branching effort, you should write all these things, okay? But to here save some time, I am not writing all these things because I have already written everything in the first example. So it is basically pi of this G. So if you do that, so it will be for this one, okay? So let me also write here, this G is 4 by 3, here G1, this G2 is 5 by 3, right? This is 3 input NAND, this is 2 input NOR, so here also it will be 5 by 3, right?
Shouldn't T2 also be 4 by 3?
Which one?
Nothing, sir. Sorry.
Okay. 4 by 3, 5 by 3, 5 by 3, right? Okay, so it is 2500 by 27, right? So then path electrical effort, right, along this path, what is this effort? So it is basically C out in this path by C in the, like, along this path. So C out is 45 by C in is 8. Fine. Now we have to write it here, path branching effort. So it is capital B. So it is, again recall, it is the pi of all this B, right? So what is the B or branching effort at this node? Can anyone tell what is the branching effort at this node? And after that, what is the branching effort at this node?
3 and 2.
Okay, yeah. What is the, for the first one here? What will be the value of B here?
3.
3. Okay. Could you please explain like how you are getting this number 3?
The C on path is X and C off path is 2X.
C on path is
X and C off path is 2X basically.
okay. So it is basically then X plus 2X by X. That's what you are saying.
Yes.
Right. Okay. Fine. And what is this B here? Branching effort here?
2.
2. Right. I hope all of you have understood. If not, please let me know. Okay, so you have understood this one. So here the branching effort is 3, here 2. So it is basically pi of this B. So it is 3, 2, so it is 6. Okay. So after that it would be the path effort, that is capital F, is equal to GBH. So it is 100 by 27, 6, 6 and H is 45 by 8. Yeah, can you please solve this thing and tell me what is the final things you are getting?
One
125.
125? Great. So it is 125, right? Now we have already seen for minimum delay, this individual stage effort should be equal to the nth root of capital F, where n is number of stages. And here, what is the number of stages? 3, right? You can see it here. 1, 2, 3, right? So this F value is cube root of 125. So which is basically 5. Then the minimum delay. So minimum delay is equal to summation of all the parasitic delay plus summation of all this effort delay. So summation of all this parasitic delay is, we have to add off the parasitic delay of this. So it is 2 input 2 plus along this path it is 3 input, so 3 plus again 2 input 2. So it is 2 plus 3 plus 2. 2 plus 3 plus 2, right? Plus effort delay. Effort delay is 3 into this total number of F. Means what is the value of F? So it is how much? 4, 7, right? 7, 3 into here 5. So I think 22, right? So this is the minimum delay, right? So the first question is solved. Find the minimum delay. The next question is size each gate for realizing the minimum delay. So interestingly, we have actually first we are finding what is the minimum delay. Then from there we have to do couple of things, right? And to find this y and x. So it is again quite simple. We have already done this thing. So it is called the gate sizing. Gate sizing. So y is equal to, again we'll start from this gate, right? The last gate, because we know here the C out. So C out is 45 into the G is 5 by 3 for 2 input NOR by 5 is the value of F, right, which gives me 15. Then you have to find the value of X, so which is, yes, this 15, because it is driving a gate which size is 15, like total cap is 15. So okay, here is the something interesting. Yeah, so for this gate,
Shouldn't it be 30?
right. So for this gate, okay, we know what is the value of y, right? But this gate is driving actually two of these gates, right? So here you have this 15, here you have 15, right? Total then load is 30. So total is 15 plus 15 into, it is 3 input NAND, so its G value or logical effort is 5 by 3 by the value of F. F is 5. So if you do that, that would give you 10. Right. Now after that, it would be type of again straightforward. Now no, this is also done. Now find the PMOS and NMOS of each transistor. So can you not find? Now what is, now you know what is the value of Y. Okay, you have to write what is the PMOS ratio for 2 input NOR gate, and from there you have to find. So let us do only one, but we will not do for all these things. Okay, this is homework. So now here we have to do the transistor sizing. So for transistor sizing, it is PMOS, NMOS. We are considering the last. This is 3 NOR, right? 3 NOR gate. So for 3 input NOR gate, what is this PMOS and NMOS ratio? Anyone?
Sir, it
Anyone?
will be
Please tell
input
me.
NOR gate,
Huh? Subhayan, what?
isn't it? Was 2 input NOR gate, right? The last.
Oh, last one is 2 input, na? Oh, huh. Yes, yes. Last one is 2 input NOR gate, right? So it is 2 input NOR gate. Yeah, for 2 input NOR gate, what is the ratio?
4:1.
We have already discussed it, right? 4:1. Right. Then what will be the PMOS width? PMOS width will be the, what is the size? 15, 4 by 5, right? NMOS width would be 15 into 1 by 5. So basically it is 12, and here it is 3. Right. So now 3, after that we have to find, right, for the 3 NAND gate. NOR gate is not there. 3 NAND gate. For 3 NAND gate. Okay, just I am writing it here. So PMOS width would be equal to, for 3 input, it would be equal to 6. NMOS width would be equal to 4, because the total is 10, right? And that's what we have seen here. X value is 10. Okay, now here is a question. Can you tell me what would be the delay offered by individual stages? Like what would be the delay
Sir,
of
that was 6 and 4 or 4 and 6.
Yes, sir.
for 4 and 1 minute? For 3 input NAND, what is
W
this? What is this PMOS and NMOS ratio?
2:3.
2:3.
Right, 2:3. So here this PMOS, like NMOS ratio is higher. So you are correct, and thank you. So it should be the other way. That is, this should be 4 and NMOS should be 6. Yes. Right. And yeah, now suppose if you have to find what is the delay offered by this stage, what is the delay offered by this stage, what is the delay offered by this stage. How can you find delay from individual stages? See, one thing, the total delay is 22, right? So total delay 22, that means if you sum up this delay, this and this, you should get 22. But now the question is, what would be the individual delay, like stage wise? First stage, second stage, third stage.
So Pi plus Fi.
Huh?
Pi plus Fi for I equal to 1.
Right. So let us do just this small thing. Right. So let us do the here this small thing before we finish this part. How are you doing on time? It's around 11. No? Individual delays. Right. So now we have to find the delay for this. Let us start from here. The first one, stage 1, stage 2, stage 3, individual delay. Okay. So first 2 input NAND gate. So here 2 input NAND gate. So for 2 input NAND gate, it is D equal to P1 plus G1 H1, right? So its P value is 2, parasitic delay is 2, G is 4 by 3, and H just we want to find it like what like from the basic like whatever we have learned, right? What is H? H is the total capacitance, which is 10 plus 10 plus 10 by the input capacitance 8. So please note, remember this value what we have written, H is equal to 10 plus 10 plus 10 by 8, and I will go up and see this. See, for this input capacitance is 8, output capacitance is this x plus x plus x value is equal to 10, right? So that is why we have written 10 plus 10 plus 10 by 8, right? So this is the total delay. So if you now calculate it, it would come 7. Now here for the next stage, that is 3 input, this is also NAND gate, 3 input NAND. So we will write it as D2 equal to P2 G2 H2. So here 3 input, parasitic delay is 3, G value is 5 by 3. Again, this basically it is C out, like, right, C out by C in. So 2, it is driving basically 2 gates, right? Each gate, like this one is driving 2 gates, each gate is having size of 15. So it is 15 by 15, right? By its the value of input is this is like I think 10, right? This is 10, right? So if you calculate it, this should come to 8. Then the 2 input NOR gate, we write it as D3 P3 plus G3 H3. So this is equal to 2 plus 5 by 3. Here output load 45, input is 15. So it should come 7. Then what will be the total? Total is 7 plus 8 plus 7 equal to 22. So you can see here this value 22 unit, the total. So basically this is basically the total delay, total delay. So total delay you can see here also we have found this is the like 22 unit of the total delay, and which is basically the minimum delay. So if you do it from these individual stages, because that would help you to decide, okay, which state is, which of the stage, okay, of that path is consuming more delay or taking much more delay, right? Then probably you can identify that stage and try to do something on that stage, right? So this is also important then. Yeah, so with this I think this logical effort part we have come to almost to the end of it. Please let me know if you have any question before we start the next topic. But do practice couple of things from here, right? For example, see here we have here only one single type of gates, x. It might not be always the case, right? It might be x, it might be something else, some other size, or not even the same gate, right? You think of some practical design, it might be maybe some another NOT gate or NAND gate or NOT gate is present here. Okay, so in that case, how you will find it? So if you have understood this, so you should be able to find that. So I request to all of you, please think about it and do couple of exercise, okay, on this, right? So this is one typical example where you can see here, all the gates are same, like, same size, right? Like all the gates are same means in particular stage the gates are same and they have the same size, but it will not be the practical case, right? Always. So practical case might be that it may, like even in the next stage you might have a mixture of different gates, different sizes. Okay, so this part is also done. So please do think about it a little bit on this, and yeah, if you have questions, then otherwise we will go to the next. Okay, this is, I hope it is quite easy to all of you. Then fine, we'll move to the next one, which is quite interesting as well as quite new to us. Before that, just we will take 1 minute break. Maybe you can also drink some water, I too, and then start. Okay, so then let's start. Okay, are you with me? Anuj, Aniket, unfortunately for many of you, I did not get any response. Deepak,
Yes, sir.
yes, are you with me?
Yes, sir. Yes, sir.
Okay, great. So thank you for responding. And let us start then. So this is a new topic, quite interesting and bit different flavor compared to whatever we have discussed so far. So far we are discussing about the static CMOS design. Remember that. Static CMOS design, right? So far we have discussed about the static CMOS design. So here one inverter looks something like this. One PMOS, one NMOS, input, VDD, ground, output. That's all. Right? This is inverter. You can make some other gates as well, implement some other Boolean function using CMOS logic that we have already learned. But this dynamic CMOS logic is a bit different. First, I will tell you how the circuit, like the circuit topology looks like, general circuit topology, and then why we need, okay, or means why this circuit actually has come to the picture. Okay, what is the primary utility of this? Okay, why people have used this? Okay, so here you can see you have the input, you have the output. You change the input, immediately the output will change, right? You have a pull-up network, you have a pull-down network. Pull-up network charges, pull-down network discharges, right? Discharges this load capacitor, CL, right? We know all the details. Okay. And here we also know during charging, the output is connected with VDD. During discharging, this output is connected with the ground. So output is either connected with this supply VDD or to the ground, means Pout is either connected with means it should be connected with the supply rails at any moment, right, except the transition, right, but in steady state it should be connected with this or this, any of the supply rail, right. Here there is no concept of clock as of now, whatever we have discussed. But in dynamic CMOS design, the circuit topology looks something like this. We have one transistor which is PMOS connected above, one transistor which is NMOS connected below, and with these two is not the input that we are giving here, but we have fed one clock. So you have fed one clock signal, okay, with this, right? And in between this PMOS and NMOS, we have this pull down network. So if you want to make an inverter, the pull down network means only this. If you want to make an NAND gate, you know what should be a pull down network. If you want to make a NOR gate, you know what should be the pull down network. So this is the pull down network. So depending on the number of inputs, you design your pull down network, and just whatever you design for CMOS, the same you take that design and just place it here between this, right? So this is the typical design, like in outside is a typical design, and whatever the block you want to design, you just make the design in CMOS, just only take that pull down network, place it here, and that makes the entire design ready, and that is basically a dynamic CMOS. Okay, so that is from the design perspective. How does it look like, right? Okay, to give you a better illustration, like this is type of quite abstract, like abstract design. Okay, let us try to be more specific. Let us say that we have this function, that is f is equal to a dot b plus c bar. We have to implement this function. Okay, so we have to implement this function. So let us implement this function in, say, static CMOS first. Okay, so static CMOS, we have to do a dot b and plus c, means or c. So we are now doing the pull down network first. B, A, C, this. Okay, now the pull up part. Yes, now please help me. What will be the pull up part if you want to design this? Students, please do respond.
A and B in parallel.
A and B in parallel. Okay, very good. A and B in parallel.
Series with C.
Very
Then
good.
C is
Series with C. Please check, is this correct? Is this correct?
Yes, sir.
Okay, great. So this is basically the static design, right? Static design, right? But we have seen, if we know the static design, how to implement this dynamic part. So dynamic part is basically we have to take this pull down network, right? Place it in between. Okay, maybe I will just draw it in a bit different way. Okay, I will keep it like this so that you can also see this part. So it is VDD. This is clock. Same clock is also fed here. Both are clock, right? So this is basically the dynamic, like dynamic design, dynamic CMOS design, right? This is the dynamic CMOS design part. Okay, now the thing is that what are the difference you can observe, or why you should try to even think for, or okay, first tell me, are you seeing any advantage compared to this design, static design, and this dynamic design?
Number of
Like
transistors
which
are
law?
reduced.
Number of transistors, very good, Shubha. So obviously the number of transistor is less compared to compared to the static design. For example, here in static design, number of transistor, here how much? 336, right? So if you have two inputs, it's basically the 2n, right? N is the inputs, right? In general. So in general is basically 2n, where n is the number of number of inputs, right? Whereas if you see here, number of transistors, how much? 3, 5,
N plus 2.
right? In general, it is n plus 2, n equal to number of transistors. So everything has started from this from this point of view only, that if you have to design some Boolean function with minimum number of gates, then how do you design, right? We have discussed couple of other things. For example, can you recall that pseudo NMOS design? For pseudo NMOS design, it is even less. It is n plus 1. Can you recall pseudo NMOS design?
Yes, sir.
Yeah, pseudo NMOS design, basically you have the pull down network part and you don't have this bottom transistor, you have only one here, like this only one MOSFET here, right? So it is basically n plus 1, right? But there was a very big disadvantage in pseudo NMOS design, that was static power dissipation. However, in dynamic CMOS, that static power dissipation is not there. Yeah, ideally not there, but due to leakage, subthreshold conduction, there should be always. Even that we have seen for CMOS also, static CMOS also, we have seen that, right? But ideally, there should not be any static power dissipation like we have seen for that pseudo NMOS design. But it gives us the advantage that we can reduce the number of transistors. So that was one of the driving factor. Reduce the number of transistors. That was one of the factor, like why the design has shifted. Like people have tried to do something innovative in this field. Okay, then when we will discuss, we will also find a couple of other interesting things. Okay, and I think those things we will we'll discuss as we move forward. Huh? Okay. Now let us. Okay. Suppose I want to design an inverter, okay, in a dynamic CMOS design. How that inverter would look like? Pretty simple, same logic. We have this clock, we have this input, inverter has only one input, then we have an NMOS, this is clock, ground, VDD, and we have to take the output from here. Okay, so this is output. This output may be driving another gate. So basically it is this C output or C load, whatever you say, that load capacitance is connected with this V out. Okay, right? So as per our design, this should be circuit should act as a dynamic inverter. Right? But now let us understand how this circuit operates. Okay, the circuit operation. So here we are going to discuss about circuit operation. Okay, so I request you to please read this operation in great detail from that Rabbis book, chapter number 6, because I cannot write all the small things here. I will write the major part of it or the main part of it, the point wise, but I request you to please go through it once from the Rabbis book. It is very clearly written in that book. Okay. Okay, so in circuit operation, you can see we have introduced two transistors, right? Above and below this pull down network. We call these transistors as MP, okay, and ME. And in dynamic CMOS logic design, there are two phases, okay, of the operation. The first phase is called pre-charge. The second phase is called evaluation. So for pre-charge, this transistor MP helps. For evaluation, this transistor ME helps. Okay. Now let us try to discuss it in a little bit more detail. So pre-charge. So pre-charge means when clock equal to 0. So when clock equal to 0, that means you have given here 0, you have given here 0. Right? That makes this transistor on, that makes this transistor off. And you have a direct path from this to this output node. So that means this output will charge, right? So this output will charge through this MP, right? This PMOS. So this MP is the pre-charge transistor. Okay. So when clock equal to 0, output capacitor charges to till VDD. This output capacitor charges to VDD. So that is basically the pre-charge stage. Okay. Now see what is happening to this NMOS, not this ME. This ME, as I mentioned, it helps in evaluation. So I will write it explicitly. So this ME is called the evaluation transistor. Okay. So ME is the evaluation transistor. It helps in during the evaluation. Okay. But now during pre-charge you have given 0 here. So this transistor is off. Alright. Now say this input is 0. This input is says 0. So if this input is 0, this transistor is off. Anyway, this capacitor cannot discharge. Say now the input is 1. Okay, in this condition. So if this input is 1, now this transistor is on. But still this capacitor cannot discharge. Because these two transistors which are NMOS, they are in series. So this is off. How can this transistor discharge or this capacitor discharge even though this is on? Right? So this capacitor will be in a charged state only. So whenever you make clock equal to 0, this capacitor will charge, the output load capacitor will charge and it should be at a level of VDD. The voltage level across this should be VDD. Okay, and it does not matter what is the input state. Input state may be 0 or 1. It does not matter because the bottom transistor is off. Okay. Now the next stage is evaluation. So in evaluation, we make I think I should use different color, otherwise. Next one is evaluation. So in evaluation, we make clock equal to 1 and this AME. So when you make clock equal to 1, see what is happening when you make clock equal to 1. This clock equal to 1. So that means this transistor is now off. This transistor is on. So that means the capacitor which was initially charged to VDD during pre-charge condition, that can discharge, and that will only discharge through in it, and if this capacitor has to discharge, then both this transistor and this transistor has to be on simultaneously. This is on, right? But if this is on, this is off, right? Means here suppose the input is 0, then it cannot discharge. And say this is on, so this is also on, this transistor is on, this transistor is on, now it can discharge. So this ME is the evaluation transistor. Fine. Okay, so during this evaluation, depending on the input of the pull down network, right? Here the pull down network is only transistor. This C out discharges and V out changes accordingly. So have you understood what I'm trying to say? Depending on the input here, that is this, depending on the input. Okay, suppose now here we have made 1 and 1, so this transistor is off, so it cannot charge any further. But this is on. However, if this is only on and here you have given 0, so this transistor is off. So still this V out should retain as VDD only, at VDD level only, right? However, if you make it 1, then it should discharge and it should fall to 0, right? Okay. Now, see another interesting phenomenon. Okay, for that, say we have done the pre-charge, so the capacitor is fully charged. Please, please understand the sequence again. Say we have pre-charged it, so during pre-charge, this capacitor is fully charged to VDD. Fine, no issue in that. Then what we have done? Then we have made. Now we have gone to the evolution state. So the clock become equal to 1. So the clock become equal to 1. Evolution state has started, right? Now say the input has changed to 1. So when the input has changed to 1, this is on, the capacitor discharges. This capacitor discharges, okay, but still we are in the evolution phase. But at that time, this 1 has changed, this input 1 has changed to 0. Are you getting my point? This input 1 has changed to 0. So this is inverter, right? When the input goes to 0, the output should become high. That means the voltage should become VDD, output voltage. But see, during evaluation state, only one change in the output is possible. So during evaluation stage, if the input is changing, then the output cannot respond to that. Is this part clear to you? During the evaluation state, the output can respond only once and it cannot respond to any change within one evaluation cycle. So is this part clear to you? Okay. If yes, very good. So as I mentioned, this is the basic operation like circuit operation of a dynamic CMOS logic. And I also request you to please go through it once again from the Raves book. Okay. Okay. So let us now discuss some of the characteristics or some of the features of this dynamic CMOS design. The first one we have already discussed, that is the number of transistors. Number of transistor is equal to n plus 2 instead of 2n for static CMOS. In case of static CMOS, right? This one we have already discussed. The second one, okay. Please tell me, this dynamic logic is yeah, which one? Dynamic logic is a ratioed logic or it is a ratioed less logic? Let's see who has remembered that ratioed logic and non-ratioed logic and explain it. What? Dynamic logic is a ratioed logic or non-ratioed logic? Which one? Yes, Shubhayan, any comment?
So it's ratioed, I think.
Ratioed, okay. Ranbir, what is the definition of ratioed logic?
Sir, when we try to decrease the number of transistors,
No, no.
and we can
Ratioed,
complete with the robustness and stability.
ratioed logic is the logic where the output level VOL dash and VOH dash, they depends on the transistor sizing. That is ratioed logic. So this is not the ratioed logic. You think about it. What is the maximum value here? It reaches to VDD. Minimum value during discharge, it falls to 0. It does not depend on this. So it is non-ratioed. So this is ratioless.
So,
Hmm.
I had a question. Have we actually gone through an example of ratio logic till now?
Have we discussed about ratioed logic or not?
No, we've discussed the definition, but have
Definition.
we ever come across any other example for it?
Other examples? Okay, let's see that. I think we have. Let's see that. Yeah, so here we have discussed about the ratioed logic and ratioless logic. So ratioed logic is the logic labels. Logic labels are determined by the relative dimensions of the composing transistor. Here ratioless logic is the logic labels are not dependent on the opposite, right? Okay, so here are the examples. For example, this ratioless logic is the static CMOS that we have already done. Here this labels does not depend on what is the transistor sizing, only this VTC just changes horizontally. However, if you consider this pseudo NMOS design, this one, the here, right, depending on the sizing of this PMOS as well as this NMOS, right, your this position, right, VOL dash, this position changes,
Okay. Thank you, sir.
right, right. So we have discussed, right? Yes. Yeah. So then is no static power dissipation. In fact, you know, all our earlier discussions, Alicia, all our earlier discussion on the basic inverters, not the static CMOS. You know, prior to the static CMOS, we have done inverter with resistive load, right? Inverter like inverter with enhancement load. Even if you see any design, okay, they are either VOH or VOL dash that will be dependent on the transistor sizing. So they are all actually ratioed logic. Okay, so here dynamic CMOS, another advantage is that the no static power dissipation, right? Because you can clearly see from this design when this PMOS is on, right, this NMOS is off. So there is no direct path from this VDD to ground. Eventually when this is off, this is only on, right? So there is not a direct path between this one and this one, right? Okay. So no static power dissipation. Okay. Now maybe one more thing I will here, but before that I will ask you one thing. For static CMOS, two input NOR. What is the logical effort? In static CMOS, we have just today also we have discussed. What is the static, what is the logical effort for static CMOS two input NOR gate?
5 by
5 by
5 by 3. Okay. Now here we'll write dynamic CMOS two input NOR. Can you comment? Okay. So NOR gate two input. Clock. So here this is NOR gate, right? So the PMOS NMOS should be in parallel or series? I am trying to design the pull down network. So the pull down network NMOS should be in series or parallel?
parallel.
Parallel. Oh, we have only two input, no? Not three input. Okay. Yeah. Now, can you make a comment? This is basically the dynamic, two input NOR gate in dynamic CMOS design. Yes, please tell me. Okay, how do you define logical effort?
Sir, is it 2 by 3?
2 by
It's 1 by 3.
1 by 3. 1 by 3.
So here input is only
Input is only a. True.
A, and for NOR, this transistor sizes should be 1 and 1.
This size would be 1 and 1. Okay.
So that's why it's 1 by 3.
Okay. So let's just then go back previously here. Yeah, this one, right? So this is NOR gate, right? So NOR gate here, this is the pull down network, right? This is the pull down network, right? Okay. So here, while discussing this, we have seen that it is like 4 unit, it is 1 by 1 unit, and the capacitor has to be like, while the total means the current driving capability of this inverter and current driving capability of this inverter should be the same, right?
Yes, sir.
Right. So from that point of view, should it be 1 by 3 or 2 by 3? So okay, maybe this we have just discussed this today only. So please take some time, understand this logical effort and all these things, and this part we are just making highlight. Okay, so what should be the logical effort for this NOR gate? But if it is 1 by 3 or 2 by 3 or whatever, but it looks like it is not going to be 5 by 3, right? So definitely the logical effort is lower than the static CMOS design, right? For dynamic CMOS, it is lower. So what do you mean by logical effort? Logical effort lower means it has a faster switching speed, right? So eventually what we can write it as faster switching, right? Okay. Any other thing that you can think other than this logical effort, means other than the value of the logical effort, why this dynamic CMOS should be faster? Why dynamic CMOS should be faster? Other than this logical effort. See, it is not difficult. See, okay, let us take that example of this inverter only. Okay. If you are considering an static inverter, so it is something like this, and suppose this inverter has to drive, okay, this is suppose the input A, it has to drive another inverter, right, for static CMOS, whereas for dynamic CMOS the design is something like this. Yes. So have you noticed something between this static and dynamic? Any difference? You are not able to see any difference here?
The only clock is there.
Only clock is there, but that is true. But see, here this output,
It is driving
right,
only one.
the output is driving both PMOS and NMOS. Right. Here is where this output is driving only the NMOS. Driving NMOS only. Right? It is not PMOS and NMOS both that it is driving. It is driving only this NMOS. So like that, this is for inverter, right? Because for any other gate also you think about it, the output has to drive both the PMOS and NMOS. Right, so it is the capacitance of both PMOS and NMOS. But however, for any gate implemented in dynamic CMOS logic, one gate has to drive only the next stage N gates. So that way also you can understand it is expected to be the faster, like why it should be faster switching, like why the switching would be faster. So number one reason is this, that the logical effort is lower, and the second reason is that it is driving only this NMOS. Right? Okay. So if you have understood this part, fine. Then let me ask you one more thing. This is again inverter only, no? Okay. Then tell me, or okay, just comment on the switching threshold. Comment on the switching threshold for this circuit, dynamic CMOS. Anyone? If you can comment on the switching threshold on this, additional 1 marks for the end semester. I will note down his name and roll number, so additional 1 marks in the end semester. Okay, okay, that offer is no longer valid. Okay, now another question again. What is the switching threshold? Or what do you mean by switching threshold?
So the point where the V in is equal to V out, or the point where
The transition happens, right? Basically, in
yes, sir,
simple word, where the
where
transition
we
happens.
switch the consideration of high or low logic.
Right, right. So then from this perspective, from that concept, you try to explain where the switching should occur. Okay, first of all, the switching can occur when? The switching can occur when? Switching can occur only in pre-charge state or evolution state. Which state?
Evaluation state.
Only in evolution, right? Pre-charge means always whatever be the value previously does not matter. Pre-charge means you give the pre-charge signal, always the output will be charged to VDD only, right? So the output can change depending on this input, this A value of A, right? On only in the evaluation state, right? So now tell me, for what value, what voltage level value of A the output can change?
One.
1. 1 means 1 volt.
No, sir,
Logic high.
Logic high. So logic high means suppose VDD is 5 volt. Then I have to give 5 volt. Are Baba, switching threshold means what? Where this will start falling. Right, when this will start falling, right? Precharge means it is always been charged, na? CL is always been charged during precharge state. Now in evolution state, when for what value, what voltage value of A, this will start falling. So this is this voltage of A. This is V output. At what voltage?
VTH.
T?
VTH.
VTH, very good, Subhayan. Right, VTH. See, this transistor during evolution state, this is like it is 1, so this is cross. This is 1, so this is on. So this transistor is is already on, right? So just you have to turn on this transistor. So just turn on it little bit. This will discharge through it. Right, so the transition will occur as soon as you go make this this voltage level of this input A near to this VTN, right? So switching threshold is near to that of this VTHN. Okay, so if then I draw this V out versus V in, say this VDD is equal to 2.5 volt and VTHN is equal to 0.5 volt. So this 1.5, 1.5 to 2.5. Okay, so it is 0.5, 1.5 to 2.5. And here also this say 1, 2 means 1 volt, 1.5 to 2.5. Okay, and say the voltage level is here. Right. So around this 0.5 it will start falling. Right, it will start falling. Right. So from this, can you comment on the noise margin? Please comment on the noise margin from this plot. Hey, I am not getting any response. It is not good actually. Can you comment? Can you not comment on noise margin high, noise margin low?
Noise margin high increases.
Noise margin?
High increases.
Noise margin high increases, right? Noise margin high is significantly higher compared to that of noise margin low. Isn't it? Because you can see this, right? So it is only this much. Right here you have this much space. Right. So, but in our actual design, we have always tried to make the noise margin high and noise margin low as means equal, like almost equal. Right. But here that issue will definitely means that issue will definitely be there, right? So then with this basically you can say these are the issues, right? That probably that you can consider here. Right. Then what about the power? Power consumption, if you are considering only for this A and this, that is one thing. But the other thing is that, okay, say you want to make this gate drive faster. So that means you have to make this transistor size bigger, right? So that it can charge faster. But when you make this transistor larger, then its input capacitance will also become higher. Then the clock will also take some power, right? Then to drive this or make this gate turn on, right? This clock have to use or spend significant amount of power to turn this clock on, right? So that way power consumption is, even though the static power dissipation is not there, that issue is not there, but the power consumption means the dynamic power consumption is not at all towards in a lower side, but it is towards in a quite higher side only. Dynamic power dissipation issue. Compare it with static CMOS design. Okay, so please do compare it with the static CMOS design and see how does this thing can be compared or linked with that of static CMOS design. Right. So these are some of the issues. Other than that, there are other issues. For example, the signal integrity issues. Okay. For example, charge leakage, charge sharing. These are the quite two prominent leakage issues. Okay, or signal integrity issue in dynamic CMOS circuits. Okay, so maybe it's already 11:52. Maybe you have definitely have some class from 12. So maybe you can we'll stop here today, because if I start the charge leakage, it will be I cannot finish it. It will take some time. Okay, so we'll start from there. The signal integrity this integrity issue in dynamic CMOS design, and in the next class, and we'll start our like discussion from there itself. And today I will share these PDFs like as I always do after this. Yeah, if you have any question. No question. Okay, then let us stop here today. So we'll start from this part, that signal integrity issue, in the next class. Okay then, thank you.